Okay, hello everyone. And today we're going to talk about the gamma and the beta distribution, okay? So let's get started. So, the motivation. The family of the gamma is a popular model for random variables that are known to be positive, okay? And what is exceptional about that? Because the family of the exponential distribution is a subfamily of the gamma distribution. So, you may ask, what is the family of the exponential distributions? Okay, so this one is a little bit technical term. It's something like the umbrella term for all distribution that we talk about, the binomial, the exponential, something all. Many common distributions, except let's say normal. Okay, I think except normal, I guess, correctly. Okay, so this is a subfamily of the gamma. Said simply, the gamma distribution is a generalization of many distributions. And the special case of the gamma distribution is the exponential distribution. The exponential distribution is the times between successive occurrences in the Poisson process. Okay, so let's get started. This is the gamma function. Okay, so the parameter is alpha. Alpha is here. Okay, the alpha is here. Okay, and this the definition. So gamma alpha is alpha minus 1 times gamma alpha minus 1. Okay, so I think you're going to use bypass integration. So nothing about the probability here. Okay, so I use the bypass integration, and you click get this one. Okay, and gamma n is n minus 1 factorial. Okay, so you could use this one to simplify this one. Okay. So it's a little bit messy, but not difficult here. So the example, evaluate gamma n plus 1 half. Okay, so because in this case we talk about a positive integer, but somehow the gamma function is the generalization of the factorial. So you can find, let's say, somehow like the factorial of the fraction number, and this one shows the example. Let's see, we're going to gamma n plus 1 blah blah up until gamma 1 half. You cannot extend it further, right? So this one is a thing that you have to find. So the gamma 1 half is integrated from 0 to infinity of square root x e minus x. But we could use some kind of creativity here. Okay, some kind of creativity that you could use this one. Is the substitution. Okay, dx equal to y dy. And you could substitute x here and substitute dx here. If you can define x and y to be in the relation something like this. Okay, and then we could get gamma 1 half. Gamma 1 half is gonna be something like this, and this one look familiar, right? It's a normal. Look at the video in the previous lecture. It is a normal. So it is equal to the square root of pi. Okay. The result is that for each alpha greater than 0 and beta greater than 0, this integrate is going to be equal to this. So this is the normalization. Because what? Because this is not the probability distribution yet. Okay? But if we divide it by this, let's say you could get something like this. It's equal to 1, right? And then you could use this as the PDF. And this called the, then this why the gamma distribution is called gamma. because it comes from the gamma function. And this guy is the proof. Okay, so let's say use the substitution, but you can do this at home. Okay, and this one is the gamma distribution. Let's say, as I said before, this one is a normalizer. It's a normalizer, okay, and this one is what we have talked before. So the thing is that the support, okay, the support of the gamma is when x greater than 0. So the normal is kind of like anything could occur, right? Anything could occur in the normal distribution, but for the gamma distribution, we are going to restrict that to only what? Only the positive side. Okay, and this is the gamma distribution. Next one is the properties of the gamma distribution. Okay, so this one you could find e to the power of x power k, okay, and then you get es squared sub s, and then what? And then you could get the, what do we call, the MTF, okay, the MTF, the similar process that we have talked about it before. Okay, and then we talk about the sum of the random variables. Okay, if the random variables x1 to sk are independent and x1 has the gamma distribution with parameter alpha I and beta, so the common distribution is beta, right? Then the sum x1 plus magnitude sk has a gamma distribution with this parameter. So let's see the definition of the MTF. The power what? The power is alpha, right? So if you have the beta in common, and we have to say alpha 1 plus until alpha n because they are independent, right? So if you have the beta as a common factor, and we have different alpha I, then you could still get the gamma distribution with the different parameter. Okay, and the special case of the gamma distribution provide a common model for phenomena such as waiting time. And this one is the exponential distribution. The exponential distribution, let's say let beta greater than 0. A random variable x has the exponential distribution with parameter beta if x has this distribution. So previously in the gamma distribution we have both parameters, right? Alpha and beta. But for the exponential distribution we have only beta. Okay? And we can prove that the exponential distribution is the interval between each occurrences in the poisson. Okay, so if you want to study the stochastic process, this one is gonna be proved for you too. Okay, this is the overview. So this one, the exponential distribution with parameter beta is the same as the gamma with parameter alpha equal to 1 and beta. So we get rid of one parameter. And if x has the exponential distribution with parameter beta, then you could get ex, variance of x, and what? And the MTF too. And this one is the memoryless property. The same basic stuff. So instead of thinking x as a number of tiles, thinking x as a time interval. Okay, the time interval. So let's say this is time, right? And then we have the t. We have the t, and have the t past h. So if t has passed already, so this one is called what? It's called history or memory. Okay, and the probability distribution that h greater than or equal to t plus h. Because t has passed already, okay, and it doesn't occur yet, the next event doesn't occur yet, it is as if we haven't been waiting for t time period to the left. It's just as if we start all over again. it's just we start over again. It is the same, right? So instead of thinking about x as the number of 12, we think about x as an interval. And this has an implication in the sampling survey also, okay? Because in the sampling survey, let's say you have to wait for the bus, okay? And then you wait for the bus for some time. We measure about when the bus has come already and when the next bus comes. So that's gonna be the exaggeration. Because if you have waited for some time, okay, so it is as if you haven't been waiting. Let's say, for example, if the bus comes in the post process, for example, okay, and this has an implication in the survey sampling also. If I were to teach that kind of course, this one will be another topic, okay. So this is the same intuition as the negative binomial. That's why it's called the memoryless. The next one, a little bit short section about beta. Beta function, okay, is function of something like this. So the beta distribution is to model something between 0 and 1. For example, if you have the P, okay, you have the, let's say the binomial and you don't want to specify the parameter yet, you can, let's say that, oh, this parameter I do not know yet, but I know that it's gonna follow beta function, beta distribution that we are going to talk later, okay. And it's the beta distribution. The beta distribution, the support. Let's say the support is between 0 and 1. That means if you have the binomial distribution where the P you are not certain yet, you can say that, oh, the P follow distribution and you will adjust them following your observations, okay? And beta distribution has two parameters, alpha and beta. It depends on the prior knowledge, okay? And these are the properties of the beta distribution, okay? We have e to the xk, e to the x, and rest of x. This one, I think, is a little bit messy, but not difficult. You can look at it into the textbook, okay? So these are the overview, okay? The fast overview of the beta distribution, the gamma distribution, and exponential distribution. And in the next video, we are going to visit a few more examples of distribution yet before we conclude this chapter. And stay tuned.